Invitiamo i gentili ospiti a prendere posto, l'evento sta per iniziare. Grazie. Buongiorno a tutte, buongiorno a tutti. Un caloroso benvenuto da parte dell'Università di Padova nell'Aula Magna Galileo Galilei, qui a Palazzo del Bo, e online sul canale ufficiale YouTube dell'Ateneo per chi sta seguendo l'evento in streaming. Fra poco ascolteremo la lecture di Carl Wieman, professore di Physics and Education alla Stanford University, e vincitore nel 2001, insieme a Eric Cornell e Wolfgang Ketterle, del Premio Nobel per la Fisica. Siamo lieti di dare il benvenuto al professor Wieman nel nostro Ateneo. Invito ora al podio per i saluti istituzionali la professoressa Marina De Rossi, delegata dalla rettrice alla formazione degli insegnanti e alla didattica innovativa.
Buongiorno a tutte, buongiorno a tutti. Porto i saluti della rettrice in questa occasione molto importante in cui abbiamo l'onore di avere il professor Wieman qui tra noi a parlare di un tema molto importante che ovviamente accanto a quello della ricerca richiama un'altra missione fondamentale per la nostra università, che appunto è la qualità della didattica. Il nostro Ateneo è da molto tempo che si occupa con impegno, con costanza e con il coinvolgimento di una grande comunità per rispondere alle esigenze della formazione e agli obiettivi che una buona didattica di qualità possono dare, sia sul piano anche della ricerca, cioè nella formazione durante il percorso universitario a una consapevolezza importante rispetto agli aspetti più profondi di una disciplina, ma anche e soprattutto per quanto riguarda poi la formazione e la preparazione delle nostre studentesse e studenti per essere pronti alle sfide del mondo del lavoro. Oggi in particolare il nostro ospite parlerà di un tema molto importante che è quello della qualità della didattica nell'educazione alle STEM, a quell'intreccio di discipline tra scienze, ingegneria, matematica, fisica, tecnologie, come dicevo proprio un intreccio interdisciplinare e trasversale che richiede conoscenze integrate ma anche competenze sviluppate a livelli superiori. Ora questo dal punto di vista metodologico per chi insegna è una vera e propria sfida. Una sfida che direi parte sin dall'età più giovane. Noi parliamo di educazione STEM, abbiamo avuto proprio la settimana scorsa un convegno importante con gli insegnanti addirittura dalla scuola dell'infanzia. L'educazione alle STEM è un percorso lungo, è un progetto importante che investe tutti gli ordini e i gradi scolastici. Ringrazio in particolare l'impegno dei colleghi delle colleghe del Dipartimento di Fisica, che tra l'altro come la matematica sono discipline che hanno proprio dei settori dedicati alla didattica, per l'impegno profuso e la costante testimonianza nella nostra comunità di quanto effettivamente la didattica possa essere integrata e arrivare appunto a colmare quelle sfide che ci poniamo. Quindi buon lavoro a tutti, grazie.
Grazie, professoressa De Rossi. Prende ora la parola il professor Flavio Seno, direttore del Dipartimento di Fisica e Astronomia Galileo Galilei. L'evento prosegue ora in lingua inglese.
Good morning. It is a great honor for me to welcome Professor Carl Wieman on behalf of the Department of Physics and Astronomy, which bears the name of this lecture hall, Galileo Galilei. Carl Wieman is one of the greatest physicists of our time. He studied physics at MIT and he earned his PhD at Stanford. He has conducted extensive experimental research in atomic and optical physics, and in 1995, together with Cornell, produced and observed the first Bose-Einstein condensate, a discovery that earned them, along with Wolfgang Ketterle, the Nobel Prize in Physics in 2001. For those who are not physicists, it is worth mentioning that Nobel Prizes are often awarded for highly specialized research and topics that may not be known to many other physicists. Not all physicists, for example, are familiar with spin glasses, a subject studied by Giorgio Parisi, whom we awarded an honorary doctorate in this very hall just last year. However, when Wieman, Cornell, and Ketterle won the Nobel Prize in 2001, they managed, with an highly advanced and difficult to replicate techniques, to demonstrate the existence of a Bose-Einstein condensate, something that was predicted in 1924, 100 years ago, by Albert Einstein and Nat Bose, and that all physics students know by their third year. With a beautiful experiment, they show a result that everyone had been awaiting for 71 years. So we can say that the Nobel Prize in 2001 was a somewhat special Nobel Prize, and we are proud to have one of those heroes here with us today. His current intellectual focus is now on undergraduate physics and science education. He has pioneered the use of experimental techniques to evaluate the efficiency of various teaching strategies for physics and other sciences, and served as Associate Director for Science in the White House Office of Science and Technology Policy. Our department is making a great effort to innovate its teaching, thanks mainly to the valuable collaboration of Marta Carli and Ornella Pantano. We believe that this is extremely important at a time when our study programs are becoming increasingly international and we have to teach physics to students with very different backgrounds, using new technological tools with which, very rapidly, the pandemic has taught us to work. A new great challenge for all teaching, and in this field, Professor Wieman was certainly been a forerunner. For this additional reason, we are deeply proud to be able to attend this lecture today. Thank you, Professor Wieman.
Our next speaker is Dr. Marta Carli, a researcher in the Department of Physics and Astronomy.
Dear colleagues, students, and all participants, both in person and online, thank you for joining us today. I would like to welcome you all on behalf of the research group in Physics and Astronomy Education, and I would like to thank them all for helping me organizing this event, and I would like to name them: Eva, Stefania, Lucia, Ornella, and all our colleagues. Today, it's my privilege to introduce the talk of Professor Carl Wieman, who is well known in the physics community, as Flavio wonderfully commented on, as one of the recipients of the 2001 Nobel Prize in Physics. Over the past 20 years, Professor Wieman's research efforts have been devoted to improving the quality of undergraduate science and engineering education through rigorous experimentation and analysis. And his research group has actually demonstrated the effectiveness of active learning strategies in improving student achievement and fostering a deeper understanding of scientific concepts. It's worth mentioning that Professor Wieman's work has had a profound impact on educational institutions around the world. And the results of his research are presented in several research articles and in his book, Improving How Universities Teach Science, published in 2017. Today, Professor Wieman will share his insights in a talk titled Taking a Scientific Approach to Science and Engineering Education, combining research on how people learn with careful experiments in university classrooms. He will show how to implement the principles of active learning in science and engineering courses. Please join me in welcoming once again Professor Carl Wieman and thanking him again for being with us today.
Thank you for that introduction. It's a great honor for me to speak at such a prominent and historic ancient university, especially almost in the room of Galileo. So, so as I said, I'm going to talk about taking a scientific approach to science and engineering education. And I just want to start by kind of making the point that my goal, and I don't see the appropriate educational goal, is not to turn all students into scientists. But in the modern world, I think it's important to have a reasonable scientific literacy for all students, just because this helps them make better decisions in many aspects of their lives and jobs in the world we live in. So today, what I'm going to, the organization is I'll start with a general introduction about how the brain learns complex thinking like a scientist or engineer, and then focus in on applying these principles in university classrooms and showing some experiments and measuring results. And then I'll focus in tighter, talking about detailed findings from classroom research showing what improves learning and why. And this is sort of primarily kind of targeted at the teachers, but there are lots of students in the room, and I think you'll also see how these ideas can help you too. Now, before I start in this, I wanted to give you a little bit of background of how I got involved in this education work and sort of my perspective on this work. And it came about not because of my classroom teaching. It actually came about because of my atomic physics research and working very closely with many PhD students in that work, and seeing what was to me a puzzling situation, which was that these students would consistently come with many years of success in their physics and mathematics courses as students, undergraduates, but when they came in to work in my lab, they really didn't know how to do physics. But it was clearly not some fundamental deficiency with them, because after a couple of years working in my laboratory, they'd turned into expert physicists. And when I first saw this happening, I thought it was just a peculiarity of individual students, but I saw it happening repeatedly, and I decided there was just a fundamental scientific question there, and which I then started to investigate it like I would a physics problem, looking at the research on how people learn, particularly on how they learn physics, to understand this puzzle of how students were consistently doing well in courses but not learning how to do real physics. And after a couple of years of reading research papers on this, I understood this explained the puzzle, but it also made me realize there were much more effective ways to teach than what we were using in most of our classrooms. But it also got me interested in this whole idea of doing education research in science. and doing experiments, collecting data, and developing basic principles, so rather similar to doing physics, but applying to education. And so, now it's many years later of doing that kind of research, but I've continually had my primary focus is what I would say expertise, understanding what it means to think like a good scientist or engineer and how one best learns that way of thinking. Now, the good news is that over the past couple of decades, there's actually been major advances from 3 different research areas which give us new insights on how to learn and teach this kind of complex thinking. And it comes from the cognitive psychologists who, mostly in the laboratories, study the basic processes of how people think and learn. Most recently, some brain research is also telling about this. And then there's the work of people like myself, physicists, biologists, chemists, in university science departments actually doing experiments in their classrooms and collecting data on this. Now, just as a note in passing, I'll say that we really have the best data on what kind of teaching is most effective and why at the university level, but for those who are interested, it's pretty clear that the ideas apply quite well, at least at the high school level and possibly below that. So let me start with sort of the most fundamental change that this research tells us, which is it's really rethinking the basic process of how this kind of learning happens. Now, the old and still quite pervasive current model at the university level of how learning works is that we have these student classrooms or student brains, and they come into our classrooms and they vary in different ways, and we immerse those brains in knowledge, and it sinks into different amounts depending on the condition of the brain. And so with this model of learning, then the focus is mostly on trying to do lots of testing and so on to select the brains that are going to absorb knowledge the best and decide what to put in that knowledge soup, what topics to teach in what order. And then if it doesn't work, blame it on the K-12 education system. That's also usually happens. So although this model is, as I say, very pervasive in universities, it's just plain wrong. The research makes this really quite clear. And the research-based view of this learning is that these brains, at least at the university level, start out not all that different, but they change as a result of their education. There's a transformation process. The neurons are really rewired, hooked up in different ways, and as a result of the intense thinking of their education, and the brain really changes and develops new capabilities as a result. And one can actually see this in modern brain imaging. I just have an image here of 2 people interpreting medical x-rays while in a functional MRI machines, looking at their brains. And you can see on the right is a medical student who's first learning how to do this. On the left is an expert radiologist who's spent many years, becoming an expert in this. And you can see that their brains are activated very differently as a result of this task. And this is just one indication of how the expert brain has really changed from the original novice brain. And so what this says is that the basic level is that learning is really about enhancing the relevant neuron connections to make the brain essentially better and stronger at what it does. And it's also that fundamentally, the brain really learns what it practices. And so it's much more like muscle development than people used to think. And so just as with a muscle, if you want to make it stronger and better, you have to exert it strenuously, and you have to do that over a long period of time. You have to do the same thing with the brain. And so the intensity and type of exercise, in the brain's case, mental exercise, that you give it is really critical for determining how it learns. And so researchers, myself and many others, are always trying to figure out, actually, the most effective ways, the most effective exercise for the brain to have it efficiently develop new skills. Okay, so that's the sort of big picture. Now I'm going to focus down about showing how to apply some of these principles in university classrooms and what kind of results we see. So the first is one experiment I had some involvement in which we're looking at the learning of a very large introductory physics class. And so we could have 2 different sections of it with 270 students each, where we'd carefully measured the student populations were very identical between the 2 sections. And then they were taught in 2 different ways. The control section was taught by a highly experienced, highly rated professor, but he used the fairly standard lecture approach, like most of you are likely familiar with. Whereas the experimental section was taught by someone who was a fairly new PhD, but trained in the program I ran in the principles and methods of this kind of research-based teaching. And these 2 instructors then agreed to cover the same body of material in the same amount of class time, and then they gave both sections a surprise quiz to test how much they'd learned from these lectures. So I assume you know what the standard lecture was like, the instructor's standing up there talking, and the students are listening, taking notes. The experimental section, though, the way it worked was, first, the students had a short pre-class reading assignment just to learn basic facts and terminology that they could be prepared to work on in class without having to spend class time on such basic information. And then class would have them work on problems or questions. An example here is one where they're given the circuit here with light bulbs and a battery, and they're asked to predict what's going to happen to the brightness of this bulb when this switch is closed. And they're given 4 different options here. And in this case, we use some technology to make sure all students are involved and to allow the instructor to probe how the entire class is thinking. And so each student has a little device called a clicker, or nowadays we usually replace this with mobile phones, where they submit what answer they think here, and the instructor's computer records who they were and what answer they chose and can see those answers. Now, so the students first give an answer, but then they're not told the solution. Instead, they're told to discuss this with their neighbors, and in a big lecture theater, so that's basically the students just sitting on either side of them. They're supposed to discuss what the answer is and why, and then they re-vote. And while those discussions are going on, the instructor isn't just standing waiting. They're circulating up and down the aisle, listening in on these conversations, getting little snapshots of what's going on in the students' brains, how they're thinking about this material. Then after the students have had a discussion and voted again, then they've done a demonstration, show the result, and then very importantly, there's then a follow-up summary from the instructor giving the students feedback on which of their models and thinking were right and which were incorrect and why. And I emphasize that because one of the things we cognitive psychologists tell us is that most learning takes place when you learn what's wrong about your thinking and how to change it and improve it. Now, so there were lots of questions like I showed you of sort of concepts, but this also involved more mathematical things where the students also had worksheets where they actually had to write out answers again, but doing it while discussing with their fellow students. And so if you think about what the students are doing during this time, you can see they're practicing thinking like physicists. You know, if you look at that question I gave, they have to choose a model for how electricity works and then apply it, in this case, with light bulbs and batteries here. And they then have to test their conceptual model by comparing it against what happened and critiquing their model and those of their fellow students in the discussions. So these are kind of all the basic thinking that you would do as a physicist. And while they're doing that, they're getting multiple forms of feedback to help them improve that thinking. They're getting it from their fellow students, they're getting it by comparing their prediction with what the demonstration showed, and they're getting it from the instructor, who's much more informed about their thinking from listening to them and seeing the vote that they've done in class. Okay, so remember this was part of a research study, and so there was this surprise quiz given to to both sections right after they'd covered this material to see how much they'd learned. And so this is a histogram of the scores, the number of students on each scores on this test, and you can see there's a profound difference in the learning between the experimental section and the standard lecture. Now, the difference is actually a little bigger than you might appreciate, because on this particular test, random guessing would give a person about 3, and so you have to think the amount of learning is sort of how far above 3 they score. And when you see that, you realize that the learning from the lecture was really small, and we have many other examples of this where we've measured this. But I also want to stress that in addition to that, the entire population the entire distribution is higher in the experimental section. And this shows that these techniques don't just work more effectively for the top students or for the bottom students. They really improve the learning for the entire distribution of all students. Okay, that was a physics example. Let me switch to a different field here. This is computer science, and this looked at the same instructors simply changing their teaching. So these are the 4 instructors who taught the 4 core introductory computer science courses at University of California at San Diego. And they had been teaching the course using a standard lecture approach, and then they all got together and they converted their teaching to this so-called research-based teaching, where it was very much like what I just described for physics. They would pose questions to the students in class, the students would discuss with each other and answer them, etc. And in this class, they didn't measure learning directly. Instead, they were focusing on what the drop and failure rate was from the course. And as you can see, across all 4 courses, the failure rates went down dramatically. And so this is an example where you have the same instructors and where they've just learned better teaching methods, and now they have 1/3 the failure rates they used to have. And they've tracked these students going on into their future courses, and all of these students are being successful in pursuing a major in computer science. Now, most of the research in general in science education has focused on these large introductory courses. That's where most of the students are. But there's now some work, and my own group has been a leader in this, looking at more advanced courses and showing how the same basic ideas can be applied to work well in advanced courses. So these are, advanced courses, for example, physics students. They're smaller classes. You can see examples. But the students generally are working at worksheets where they have to fill things out and complete, but they're working in small groups with the instructor in the background. You can see moving around, monitoring how they're doing, answering individual questions, and so on. And we've shown that also leads to substantial improvements in learning compared to the lectures. And just make the point that now at Stanford in the physics department, we've converted now almost all of the undergraduate physics courses have been converted to this kind of research-based teaching. And we even have examples of people using this in graduate courses with great success. So all of these classes I'm talking about have the same basic structure where the students do some kind of modest preparation before they come to class. Then the instructor introduces the topic and what they're going to be doing for the day. And then the students work in these small groups on different answering questions, writing things out, talking to each other, while the instructor is going around monitoring the groups, listening to their conversations, seeing how they're working on things. And then periodically, typically after 10 or 15 minutes of work like this, the instructor will then bring the class together and essentially give them feedback on their thinking, provide them, maybe answer questions, maybe provide them with new information, knowledge they might need to solve the problems with. And that goes on for several minutes, and then the students will then return to the next section of the activity. And so the two essential features that are going on in this way is that you have the students are busy thinking. They're practicing the expert reasoning and knowledge use that you want them to master. And you have the instructor is much more knowledgeable about their thinking, and so can be much more effective in targeting the feedback that's provided to them. And I'll just make a note in passing that we worked with, I'll say at the end, a program that made very large-scale changes with hundreds of instructors adopting this kind of teaching, and overwhelmingly, the instructors just found this a much more rewarding way of teaching than they did when they had previously been lecturing. So those are just a few, some of my favorite examples of research, but you can actually find almost 1,000 studies from across all different fields of undergraduate science and engineering where they've compared this kind of research-based teaching with traditional lecture. And the consistently research-based teaching shows greater learning and lower failure and dropout rates. Okay, so let me move on now to really focus in tighter on very specific aspects of education research that can be, if you're a teacher, can be used directly in your instruction. And if you're a student, you can sort of see how these ideas can apply in your own learning to help enhance it. So this figure is my attempt to sort of summarize all the research that's been done in the field of kind of, having people learn to think like a good scientist and engineer, what research findings are important. And the core of this is really at the center. They need to be practicing solving problems with good feedback on that. And good feedback means it needs to be timely and specific and actionable, so it really guides the student in what to change to be better. But there's then a lot of things that have to go into designing the practice tasks, and that's the boxes along the top. And then there's some things of research on how to implement these in the actual classroom. Those are the boxes on the bottom. And so I don't have time to go through in detail all of these things, so I'll just give you some highlights from selected areas. But I do want to make the point that I think this body of research really defines teaching expertise in a way you couldn't have done 20 years ago. And by that, what I mean is it really identifies now the practices that research tells us if an instructor is knowledgeable and applies these things, they will consistently produce better learning than if they don't. Okay, so let me start with, in these practice tasks, you have to embed the disciplinary knowledge that you want the person, their expertise you want the person to learn. And so what goes into that? Well, here I'm going to refer back to some research my own group has been doing, looking at how experts across the fields of science and engineering solve authentic problems in their field. Excuse me. And we found that their problem-solving process is really defined by making a series of decisions with limited information. And the thing that was most surprising to us was to find that across all of these different disciplines, they make the same basic set of decisions in problem solving. These are things like deciding what concepts are relevant to solving the problem, deciding what information is relevant, what's needed, how to find it, deciding what approximations and simplifications are appropriate, and so on through the whole list. And when you see the decisions laid out like that, it makes more sense that how these are going to apply in many different subject areas. But although the decisions themselves are general, the process of making the decision always calls upon specialized knowledge in the discipline relevant to the particular problem. And so that's where the person has to learn the knowledge they need from the particular subject area to guide those decisions. But this knowledge we see in experts is always organized around its use for making decisions, and that's the best way to learn it. And so just kind of to summarize, what this tells us is that learning expert thinking in a subject area requires extended practicing, making these kind of problem-solving decisions in the context of some authentic problem in the discipline, and acquiring and using the knowledge and reasoning of experts to make those decisions and solve problems. And so that really is what needs to go into the design of the problem-solving tasks. So I'm going to, just to give you a little better idea of what these kind of decisions are, because I think they're really critical to build into the instruction. I'll give just a minute to skim through these and before moving on. Okay, you may not have gotten through all of them, but you've got a better sense of what kind of things they are. And the point of this is, if you're a teacher, you really want to make sure that you're having your students have to practice making these decisions If you're a student, you really want to be thinking about, as you're learning and solving problems, that you're explicitly thinking about at the decisions you have to make to be a good problem solver. Now, one of the things that's striking and of concern is we've done analysis looking at a bunch of different physics courses and the kinds of problems the students are given in the course. And without going into details, we find that typical physics problem courses problems have involved very few of these decisions. And so students are learning information, but they're really never learning how to apply that information to solve problems in a meaningful way. Okay, let me move on here to the middle part here, the prior knowledge and experience and motivation. These are tricky areas because these depend a great deal on the student's background experience, and there's lots of student variation. And so it makes it challenging to know how to do it perfectly. But some basic things we know is that it's important in teaching to connect up and build on the learner's prior knowledge and experience. And what that means is that you need practice tasks which are challenging based on what the learner knows, but not impossible. So they're hard but doable. And of course, that varies with the different backgrounds of the learners, and so can be a challenge in instruction, but that's the goal you need to strive for. The motivation aspect, I think, is often perhaps taken for granted at the university level, and it's really, that's a bad thing to do, because we know from a lot of studies that motivation is a tremendously critical part in learning. And there's one could say a lot about this, but there's just a couple of basic points I want to make here, which is that some things that enhance motivation, the first is trying to find an interesting, meaningful context, meaningful to the learner, to present the material in. That makes it more interesting and motivating for the learner. And then also having the learner believe that they can learn the material and how to learn the material. And so they get a sense of accomplishment as they're making progress. And these are also very important for motivating the students. Okay, I'm going to jump now to say a bit more about brain constraints, because this is something that's actually enormously important and very seldom recognized by university teachers. And this has to do with how the memory works. And it turns out people who study memory see that it's actually made up of two parts. There's the second part is the long-term memory, and this is what, when most of us talk about memory, this is what we're thinking about, and it has enormous capacity. You can remember many things, and it operates over very long duration. But in addition to this long-term memory, there's something called the short-term working memory, and this is really like a buffer that information has to go through and be processed before it can go into long-term memory. And this working memory is very different from long-term memory. In particular, it works over short-term sort of time scales of minutes, and it has a tiny capacity. For the typical human brain, it's about 6 items. So it's really how many things your brain can sort of pay attention to at the same time. But this limited capacity is very important, because what it means is that when you hear or see some new thing, it catches your attention. Basically, it goes into working memory, and that pushes out something that was in there before, and so it doesn't get processed and into long-term memory. And if it's something that you're supposed to be learning, it gets lost and you don't learn it. And so what the implication of this for teaching is that any additional item that goes into long-term memory, it reduces the process and learning of what was there. And so you sort of, everything you say and present to students has a price. And if you think about different aspects of things that can use up working memory, I mean, first, the really dramatic part is the split attention. If the students are checking their mobile phones or computers, that uses up most of their working memory, and so the learning, it's just a disaster for learning. And if you're a student, I'll just emphasize, one of the problems is human beings are very bad at recognizing how detrimental this is to their learning and splitting their attention. So if you're a student, don't do this. It's really bad. And it's even worse in the online setting. But there's lots of things instructors can do that actually puts unnecessary burden on working memory. If they introduce new jargon, if they just try and cover way too many topics, as often happens in many lectures, even putting in a picture which has some nice extra features just to make it more attractive, if those catch students' attention, that actually hurts their fills up their working memory and hurts their learning. And the thing that gets the most outrage when I say it is that even these interesting little digressions and jokes that get students' attention, those actually hurt their learning because they use up working memory that could be focused on the most important material. Okay, let me now move on and finish up with some of the research on the implementation of these practice tasks in the classroom. And so you need to design good tasks, like I talked about, but you need to make sure the tasks have good deliverables, things that each student has to explicitly do, answering a question, writing down a solution, or something that they have to turn in, that they have to complete. That's just an important essential to make this work effectively. And then this learning is almost always done in small groups, groups of 3 to 4, and there's a good reason for that. There's a lot of benefits to this kind of social interaction during the learning process. And when I first talk to new faculty who aren't familiar with this, a lot of times they're very surprised at this, and they don't understand how a student talking to a fellow student could be more beneficial to their learning than listening to the expert instructor explaining it. And the fact is, it really is better, and we have good data showing this, and there's a couple of reasons for it. The first is, in talking to fellow students, you can get much more individualized feedback on errors in little things you might be thinking about wrong, confused about something that a fellow student can quickly explain to you, whereas you're not going to, in a big class, the instructor can't give you that kind of immediate direct feedback. But there's another more important and more interesting aspect of this, which has actually been quite well studied. And that is that in the process of explaining or teaching something to someone else, it actually triggers a novel cognitive processing in your brain. Your brain has a whole bunch of circuitry sort of built around social interactions that sort of kicks in if you're going to be teaching something to some students. And so there's good data showing that this process of teaching or even thinking about teaching something to somebody else produces more learning than if you spent the same amount of time just studying the material. So there's just sort of unique benefits to that for learning. And then finally, having students talk to each other is really useful as a teacher. As I said before, you can listen in on those conversations and understand a lot more about how your students are thinking than you can if you're just staring out at their faces. Okay, so to conclude this part of the talk, that I think we have research showing what's good teaching design and implementation, and it gives better learning than traditional lecture, and we understand why. Now, I want to just I was asked to say a little bit about large-scale institutional transformation. How does one go about trying to take these things from individual experiments by instructors to make it so that many instructors in an institution are teaching this way? And so we did a large-scale experiment on this where we changed several hundred science faculty, actually at UBC and University of Colorado, to adopt these better teaching methods. And I wrote a whole book on this, and so I'm not going to try and explain it here, but I'll just say some of the key results from that experiment were that we showed that this large-scale change is really possible. We changed virtually how entire departments, science departments, teach, but it really required substantial incentives and support at the department level to make that change happen. One of the results we showed was that, as I mentioned before, when faculty learned to teach this way, it did take them some time and effort, roughly 50 hours of training to learn to do this, but they then greatly preferred that to using lecture, and they continued then to teach that way. And we also showed that the ongoing instructional cost was just the same, even though the faculty were using very different methods. But to make this happen, the institution really needs to think how to recognize and support and incentivize this kind of teaching expertise that I've been talking about here. And then finally, I think one of the most critical aspects is to find better ways to evaluate teaching than the traditional student evaluations, because they really don't capture the quality of the teaching methods being used. So with that, I'll stop and we'll have time for questions. As I said, I've sort of shown you what the research tells us about good design and implementation of better teaching practices. And here's some of my favorite references, some books and some resources if you want to learn more about this. And I'll make sure that Marta somehow has my slides and can, if you want to see them to review later, because I know I've exceeded your working memory capacity probably and how many things I've talked about. So thank you for your attention.
Thank you, Professor Wieman. As Professor Wieman said, there will now be an opportunity to ask him a few questions. He will be joined by Dr. Marta Carli, who will be chairing this Q&A session. Thank you.
Okay, so thank you again, Carol, for this wonderful talk. And I now encourage a question for the audience. From all the components, I would like to emphasize this, from students, teaching assistants, colleagues, teachers, whoever is present here today. And I think there's also the possibility for those online to know, because there's on YouTube. No, so only from the audience here. Yeah, thank you, sorry. Yes.
Well, I understand that doing something else distracts. Do you hear me? Well, I understand, for instance, answering your mail or stuff like that is distracting. I was a teacher, university teacher, and why do you say a joke or a nice figure is not improving teaching?
Yeah, I always get pushback when I mention this because the teachers will say, oh, but when I make a joke, that's the time when students are really only time they're paying attention to me. And the students also complain. They say, no, when they're making a joke or story, that's the time I really pay attention in class. But that's the point, really, is that attention uses up part of the working memory. And so the students, and in fact, we've done some surveys on this, a follow-up, students will often remember the jokes the professor had and remember nothing about what the content of the class was. So, and it is just that, which is that the brain just doesn't have the capacity to pay attention to that many things. And so something that is interesting, it gets their attention, but isn't directly related to the material to be learned, hurts their learning. Now, if the joke directly involves the learning that you want them to have, then that can actually be useful.
Thank you very much for your very nice lecture. I have learned a lot from that, and I shall also thank my university for giving me and us the chance to listen to you, and also for the care it has showed in the last 8 years in going along the directions you have been telling us. Now, the question I would like to ask is related to testing knowledge. And I have two kinds of questions. The first one is on whether you have any results on the impact of active learning on the persistence over time of learning, because our time window is usually where we assess whether the students have learned or not is just the exam. The point is that will that learning remain on a longer time span if teaching was done according to active learning criteria or not? So do you have any evidence on this? The second is, do you really think that the way we test learning through exams is a way to understand whether students have learned or not? Of course, it depends. Exams in a way should be a proxy of real situations where learning is applied, but I see more and more attention on preparing exams based on multiple choice questions. Is that a proper way to assess learning, in your opinion? Thank you.
Okay, so let me answer the second question first. And, I think there's a lot of questions about the value of what tests are actually measuring in terms of what you can tell about learning. And so you're right to raise concerns about that. If you think about the, I'm kind of focusing on having students think like a scientist. Well, the exam conditions are very artificial and totally different from how a normal scientist would actually function. And so it raises a lot of questions about that. And, I know sort of my own experience when I follow up exams with interviews, I realize, boy, I'm not doing a very good job of capturing these things. On the other hand, for some of these things, in particular for the research, we have really quite carefully developed tests where what we call validating the tests by having students take them, interviewing the students afterwards to make sure they're thinking about them in the right way. And so those kind of tests are reasonably accurate, I would say, for sort of measuring learning. But, the other side of it is just with all their weaknesses, tests are sort of all we have at this point. And so we sort of have to use them as best we can. And, you know, there are a lot of things that are important about designing good tests. I think one thing I feel strongly about is you really can't expect students to think about sort of new material and new different ways. That's just an invalid thing for a test. You want to make sure that the tests look a whole lot like the kinds of problems students have been practicing already, and you're just seeing if they have mastered that. Okay, so back to your first question about long-term retention. There isn't very much done on that, much research. It's kind of hard to do because you have to track students over a long period of time. You have to worry about what other intermediate, you know, learning effects they've had. But my group has done a study of this, and we actually looked at for this, we actually had one of these carefully developed tests where we, looking at their mastery of the basic concepts in the course, and what we found was actually quite interesting, that we got data a year and a half and 2 years later, and we found very good retention, much, much better than what people have measured previously in other classes. And what we believe the reason is we were really probing basic concepts about that covered in the course. And these basic concepts are things that you because they're basic concepts, they sort of come back to repeatedly in the course, whereas other tests of long-term retention is sort of simple information that they just might get and use once or twice, and then that's quickly forgotten. Whereas we had almost perfect retention, actually. But it was interesting. That was true for the active learning course, but we also had a comparison of the same course but taught by lecture, and the students scored lower on the conceptual learning in the lecture course, but they also had the same degree of retention. So they were lower right at the end of the course, but they were just as low later on. And so that sort of suggested that for basic concepts, it actually didn't make much difference what kind of teaching they got, except in terms of retention, but there was a distinct difference.
Can you introduce yourself when you're asking a question so we can better contextualize the question that's being asked? Thank you.
Paolo Villoresi, University of Padua. I'm a physicist. I feel like joining and thank you for very interesting and stimulating arguments. And after yesterday, I've checked on the UBC website for examples, and well, I've seen the way in which using the clickers and the giveaway are very stimulating and engaging to the student, but at the same time, it requires, are you also say today, sort of a selection of the topic which end up to essentially less material that you will present at the end of the course. I mean, do you have a figure of what you have, say, to let go with respect to the standard lecturing, I mean, concept, because these things of giving the questionnaires, using the clickers is absorbing time at the end of the hour, okay, so you definitely have less time for the concept. Do you have a figure for what is essentially, I wouldn't say lost, but less, or there are countermeasures, maybe?
Yeah, so we looked at that across quite a number of courses on the time use, and it is important as you're using these methods to think quite carefully about how to optimize your use of time in the coverage. And what we saw was across different courses, considerable variation in how much people could or couldn't cover. I would say reasonably typical was about 10% less. So that they would cover about 10% less material, but had much greater learning. We have had examples actually in advanced courses where they find they're covering more material, and that's because they're spending much less time with the students sort of watching them do long mathematical derivations on the board, and instead their students are sort of working through the key aspects and decisions of the derivation, which takes less time than what they were doing before. And so in some cases, they actually cover more material. But I would say roughly 10% less would be a rough guide. But it does require paying careful attention to making sure you're using time well.
Yeah, after your questions, there are 3 questions here and another one there, and then others can raise their hands.
I'm Fabrizio Duchiero, electrical engineer. So I have a very short question. In your slide, I see only picture regarding physical classrooms. What do you think about the application of active learning on online courses? Do you have any recommendation to be more effective in such a kind of method on online courses?
It turns out that you can implement active learning in online courses, and in fact, it can well be more effective than if you have a big lecture theater where it's hard for students to interact and talk with each other. I mean, and the use in online is, we're using Zoom, we use breakout groups where the students are put into small groups and talk there with the instructor, can hop around between them. And so, yeah, it actually can work quite well there, and quite possibly better than in real life. There are other challenges with, like I say, with online. It's so easy to have students distracted with other things on their computer and so on. But I think you're right about the basic principle. And in fact, that's what for our big introductory courses at Stanford, what happened was after they had to go online, they had not previously been having these kind of active learning classes. When they went online, they had to do something better, and so they started having these, and the instructors realized, gee, this was just a lot better, having students work on problems and talking to each other. And so after we came back in person, they switched over all the teaching to just driven by that wisdom.
This side.
Hi, I am a student from a master's degree here in Padua from Physics of Data. And so thank you for your lecture. It was really, really interesting. And I really hope that in the nearest possible future, this method is going to be implemented, at least for physics. So what I was wondering is that I feel that, at least for my opinion, and also talking to other fellow students of physics, a kind of a barrier in learning is also that maybe students fear asking questions to the teacher or to the professor or to also other students, because there is maybe like the fear of saying something incorrect or stupid or something like that. So I was wondering if in your studies you have found that this active learning method also made the students feel more comfortable in asking questions to the professor, since it's kind of a less frontal relationship.
Yeah, that's a very good point. One of the first points is that when we have students going into active learning, working in these small groups, it's really important to introduce students to this idea and sort of set norms of behavior about how they should talk to each other and behave when working together in groups. And that means sort of being much more receptive and polite when responding to fellow students' questions. And we have seen some evidence that, in fact, when students are working this way, it does make them more comfortable asking questions in general. I think there's probably a couple of reasons for that. One is just they're more used to talking to each other and asking questions, and so they're more willing to ask questions in class as a whole. But the other one that I think is perhaps at least as, or more important, is because the instructor is circulating around, you know, talking individually to the groups and the students in the groups, the students are just kind of much more comfortable with the instructor. They're not such a frightening, foreign, you know, distant object, and so that makes them also more willing to ask questions in class. So we've definitely seen that happen.
I have a quick follow-up question on that. Does that happen for all groups of students, including women, other marginalized groups, or are there ways to encourage the students to ask questions?
Yeah, I mean, now there is this is a whole different area of worrying about group composition, and, you know, what we do find is that it can, for marginalized students, groups can work poorly and they sort of get shut out. We do know that it's important to have groups that don't have a single, you know, like woman or a single student of color in the group and so on. But even without that, there are times when it can be, you know, not all are participating comfortably, and that's one thing a good instructor has to do, is sort of monitor that and try and intervene to make that help, because it is a very real concern.
Sorry for interrupting.
Hello, I'm Tudor Popescu from the Department of General Psychology. So my question is actually quite similar to what was asked in the previous two questions, but I'll just ask it for the slight nuance. So you mentioned the importance of the instructor listening in on the conversation students are having, but of course there's a massive individual variability in how comfortable people are being listened in on, and even more how comfortable they are raising their hand or just speaking out, being heard speaking out. And specifically, I think here in Europe, there is a great gradient going down from Great Britain and onto the continental Europe of just how comfortable people are speaking, even in, not in a big environment like this, but even in small classes. So given that your research has, of course, the US as its center, do you think it's worth having localized versions of this kind of research that perhaps adapts better to a given cultural milieu where it is or it is not at all appropriate or, you know, common for students to be comfortable speaking out, such as this method entails? Thank you.
Yeah, I mean, that's a really good point, is that, you know, almost all our research does come from North America, and so, you know, you do worry about how generalizable it is. I will say there's growing amounts now being done internationally, and it really has been showing a lot of consistency across different countries and different cultures, more than I would have expected, to be honest. So I think there's still more to be learned, and I'm sure there are fine differences, but at kind of at the course level or the crude level, it actually has been unusually consistent. And, you know, and it may not be that surprising. Universities, you know, we have different countries and cultures, but the universities and university systems are by and large very standardized across the world, much more than most of our other cultural institutions, I would say. And so it may not be that surprising that it's kind of similar. I have to raise a comment or question here. I'm struck by both yesterday and in today, the questions are overwhelmingly from males. I'm just curious, are females scared to ask questions in Italy?
just to...
Thank you,
Yeah.
I'm sorry. Thank you, Professor, for your sharing. I am an undergrad in engineering, in computer science and electrical. So I do physics and math too. So my question is about, you said about individualized feedback of student to student. And I really appreciate the ideas, much as ideal it is. But the critical thing here is the difference between the system education in Europe, in Italy, and compared to the US. Because here in Italy, when I do courses in physics, math, it's a lot of bunch of Greek alphabet, theory on the board, and we students could barely grasp the idea of it, so it's really hard to evaluate the reliability of the individualized feedback. So most of the time I turn to my friend, this is a point of view of mine, I would turn to my friend and say, hey, are you really understand what professor is saying? And he will reply to me like, I have no idea. So most of the time we will be like that, and that story just go to nowhere. So it's really hard for professor to listen to the conversation of all of us, and it's really hard for us to explain to each other because we basically couldn't understand much to explain to each other. So I just want to ask about the reliability of the individualized feedback in maybe here in Italy when the class is really deeply theory compared to the US. Thank you, Professor.
Yeah, so I think the problem you're talking about is not unique to Italy. I think you can find the same situation in the US, but if you remember my talking about this, I was saying the in the design of the activities, they have to be matched to the learner's experience. And so that means the learners have to be able to understand and make sense of them. And if it's completely beyond what the learner is understanding, then yeah, the point of feedback is kind of meaningless because there's sort of nothing to give feedback on. And so it really, I would say, starts at the level before that of kind of having the instructor be somewhat reasonably attuned to what the students can learn and are learning, and then they can give more meaningful feedback. But if it's totally beyond what the students are grasping, then feedback is kind of pointless. And I would say that's not unique to Italy. I think you'll find that in any country at some level.
So there's now one, sorry? Yeah, there was one booked here, then you, and then the other person here. Okay.
Giovanni Colombo, a mathematician that enjoys teaching to first-year engineering students, calculus. But not only calculus, because we had the tradition to teach definitions and epsilon delta arguments, and required that students are able to repeat some of them, the easiest one. In the very first lecture, I tried to tell students that mathematics is simpler than life. What is difficult instead is the abstract reasoning, abstract arguments. And eventually, students will forget how to differentiate the hyperbolic cosine, but the abstract reasoning, ability of abstract reasoning will remain. At least this is my, I bet on this. You are not mentioning explicitly mathematics in your talk. I'm sure that there is a reason, maybe because abstract reasoning requires more time that one should spend on his or her table to let things, say, be soaked. Okay, then one small thing. When I teach I cannot look at students like at brains. Say, only a part of them. When I teach, I try to look them into their eyes, not into their brain. This is maybe why I'm more oriented towards traditional and maybe not effective lecture rather than concept of active learning that I would like to learn now after your talk.
So I'm not. Do you understand the question?
Can you summarize in a focused question for Professor Wieman? Sorry. Yeah.
Okay. So yeah, how to teach mathematics. So I would lump it together with all the different things that I was talking about. You need to think about, okay, what you want them to be able to do with the mathematics as an engineer, and the very specific sort of skills and knowledge that they're going to have to be using as engineers. And then you think about how you have them actually practicing that thinking in order to get it. And some of them start out farther ahead than others. But I think, what the general evidence would be is that almost all of them with sufficient practice can master those skills. So, but I'd say it's starting out thinking. And I see a problem in some cases of what the mathematics being taught by the math department versus the mathematics needed by someone who's going to be an engineer or scientist. And mathematicians think about math in quite a different way than the way engineers think about it as a tool to be used. And so anyway, so I think the most effective way to think about it is, okay, you do have to think about it as a tool, how to use that tool, how to decide which of these mathematical tools should apply in a particular situation and be used, and just have the students then practicing doing that. So it's maybe an overly simplified answer, but that's just a quick response.
Fosca Conti from the Department of Chemical Sciences, and I teach chemistry, I teach physical chemistry, and my question is about artificial intelligence. So just to know your opinion in relation to your very nice talk, taking a scientific approach to science and engineering education. We see already in the present the impact of artificial intelligence also in teaching and in the student. And in the future it will be much stronger, this very important contribution. So just to know a short opinion.
So my group, like many people, are busy thinking about the implications of artificial intelligence for education. And there's really two different aspects of this. One is how we can use artificial intelligence to support teaching. And some of the things we're exploring, and like many other people now, is looking at first how we might be able to use it to grade student solutions, to basically replace that painful business of where students solving problems and going through and evaluating and giving feedback to them. And so we're studying how to use these large language models, ChatGPT, to see how well it can do that, and we're getting some encouraging results. And then another thing we're looking at is how it can be used as an individual tutor. So when students are working through a problem, how it can be giving them useful feedback to help support their learning. That's challenging because what they tend to want to do is just give the students the answer right away. And that's not what a good tutor does. You know, a good tutor helps the learner understand how to change their own thinking by prompting them with questions and so on. So we're working on that, but it's not so easy. Then there's another side of this question, though, which is just the whole question about what it's going to mean to be an educated person in the world of artificial intelligence when there's so many things you can just look up that we're busy teaching students now. And so I don't really know the answer to that, but I tend to think that if you look at these problem-solving decisions, these are things where you don't have all the information, you have to make judgments about. I'm suspecting that artificial intelligence is not going to ever be very good at that. And so there's a lot of things where we're teaching students to follow procedures where we maybe don't need to spend so much time on because they'll just be able to look up that procedure for processing something, but that for making problem-solving decisions, those are probably going to stay still important for the students to learn in the future.
So there's 4 questions already booked, and I think that will be all. But colleagues will project a slide, maybe in a few minutes, when we're finished, where you can get a QR code and post any further questions or see the questions that have already been posted and endorse them with a like to prioritize them. And we will discuss those questions in a focus group that will be held at the physics department today, and then the outcomes will be shared. So if you have any other questions, please submit them and we will try to consider them. So no more bookings for questions live, but we will give now space to the ones that have been already booked. So there was, yeah.
Hi, I'm from the US. I did my undergrad in physics.
Can you put it closer?
Sorry. I'm from the US. I did my undergraduate in physics there, and I'm in the master's in astronomy program now. I had several, maybe 1 or 2 classes in the US with this format of teaching. And I was wondering why you think that professors are resistant to implementing this type of teaching program for their lectures.
So why are professors resistant? I mean, first, most fundamentally, it's just the culture. I mean, cultures are built to maintain themselves. And so you have a culture of this kind of teaching as what they're familiar with. It's what they saw, when they were in education. And people are just naturally very resistant to change, to adopting something that's new and different because of that. So that's probably the most fundamental and important. But then there are also reasons where, kind of connected with that, when they first hear about it, they always are thinking about all the problems that can come up that's kind of natural to human beings. When there's something new and different, they focus on all the things they might think that might go wrong, and so they're scared about that. And then the other side of it is just, it takes time to learn to do something new, and they're busy and they are uncomfortable spending that amount of time. So I think those are the basic reasons, but mostly it just comes back to people are mostly just a lot more comfortable doing what they're used to and don't like to change that.
Person here, it was, okay.
Good morning to everyone, and good morning, Professor. Thank you for the lecture you have taken. And I have a question about a topic you faced in your slides, which is motivation. I am a master degree environmental engineering student, and from a student point of view, in my opinion, after, for instance, a very long lecture or long years of studying as well, there's a sense of tiredness or boredness. I mean, we need to ask what are the suggestions you would give to professors and students, mainly as well, to pursue motivation, to improve motivation after a long period of term. Thank you.
So she's asking about motivation after lectures.
Yes, yes. So your question is about motivation, basically, right? Yes. So can you two, can you maybe summarize into a quick question?
Sorry. Just suggestions to maintain motivation through the years.
Yeah.
So, thank you.
I mean, you know, what we see is if long uninterrupted lectures, it's very hard for people to stay motivated to pay attention. And so, you know, breaking it up with something that students are actually doing helps a lot to kind of keep interest and motivation. But then the other things that I was talking about are just important, of really trying to think about how to make the material useful and relevant so the students can see how they could use this in their future, why it's important. And, you know, that sort of matters at all times. And so but if you have people seeing it as valuable and important and interesting, then they'll stay interested and motivated for a lot longer period of time.
Okay, so last two questions. Please try to be concise and focused. Yeah.
Luca Quairolo, Department of Neuroscience. Have you seen any changes in intelligence? First. Second, is there related to any previous cognitive capability?
So you're talking about intelligence and cognitive ability.
As your approach is very broad, this can translate larger than only learning strategy. So this can impact intelligence. And so have you measured it, previous and before and after? And second, is there any relationship between the increase in performance and their previous cognitive ability?
Yeah, so that gets into a lot of complications about your measurement tools of intelligence and cognitive ability. And so that's a very murky area. You know, one of the things I will say is in fact, almost all the measures of intelligence, if people actually practice the tasks involved, they get a lot better at it. And so, but by the same token, practicing doing something different doesn't really make much difference. And so I think, you know, we're measuring learning in science courses and how much better they are thinking about science, you know, and to the extent you've got some intelligence test that's not looking at that kind of thinking, it's not going to see any difference. If you have a test that does reflect those kinds of thinking things, the students are almost certainly going to get better, because, you know, and that's I think one weakness of intelligence tests that's very often overlooked, which is that you can just practice at them and get better at them. And so what are they really measuring, you know?
Okay, thank you. Yeah, one last question.
Professor Wieman, I'm a student. I'm an undergrad in the second year of the engineering program here,
in Padova. And I just have a general question, like the method of active teaching that you're presenting, it's, as a student, I feel like that's one of the ways that I want to be taught science and engineering. And I think that these methods need a lot of time and a lot of debates from different cultures, to be able to implement in university teaching or for a student to actually get to, being taught with this method and, get better at their STEM learning. So I just have a question. Do you have any advice for students who want to actively learn and actively think like a scientist before this method could, take control?
Yeah, so, that's a good question. If you don't have a professor who's putting this in, how can you learn? And there are a lot of things you can do as a student where if you sort of think about the thinking practice that I'm talking about here, you can do that. People naturally do that. I mean, you can go back and look over your lectures and you can think about, what were the problem-solving decisions, for example, that this material allows you to make, and how could this be used, and why did someone think about it this way? And similarly, when you're doing your studying, you can put it in that perspective of how this material could be used, what decisions. You can think about all that list of decisions I made and think about as you're solving problems, trying to break the problem up into explicitly practicing making those kinds of decisions. And so I think if you as a student, even in any class in your studying, you can put in a lot of the like I say, the thinking practice that helps you. And if you kind of look at successful scientists, most of them went through lots of lectures and they learned how to think scientifically, and it's just because the human brain has that capability, and so they're just approaching their own learning and studying that way. And so, there is a great deal that a student can actually do to make their learning more successful.
Thank you. So this was our last question. So I would just like to thank Professor Wieman again. And also, I would also to thank all the people here who helped organizing this event, both in the department and in the central unit, and all those of you who contributed with their questions and will continue to contribute. And I think that the fact that we are here from different components, instructors, students, postdocs, and from different disciplinary cultures, from education, physics, engineering, witnesses that the endeavor of teaching and learning is a common one, and we all care for that. And so I think we should continue to work in that together and collaborate and networking and put in our mind and hearts and best efforts to that. And I'm sure we will. So thank you again.